I want to go over the homework that was due on Friday for C period and is due on Monday for E and H period. I may not go over detail in class, so I wanted to make sure I provided some video solutions here for all of us. So, first, when doing energy problems, let's just remember our fundamental definition. Energy is a conserved quantity. I'm going to say it that way, which is a fancy word for a number that doesn't change at the beginning and the end of a process. And it has units of joules or newtons times meters. And so our whole purpose in doing these beginning problems with energy is that we're going to add up the energy at the beginning and at the end set them equal and then plug in specific energy formulas to obtain unknown quantities. So for example, right here, first let's label what everything is. We have a mass for this kid, we have the height, and it looks like eventually we end up with a speed. And then the word friction implies that we have dissipated energy. What I'm going to do is I'm going to put all this together with a picture. So here's a slide, and we'll put the kid at the top here. And what we'll say at the top is we know that h is bigger than 0, but v equals 0. And at the bottom, h is 0, v is greater than 0, and we had some friction acting. Putting all this together, what this tells us is that we did have Eg, there is no Ek, this is at the beginning, and then at the end, all of our Eg is gone, and it has been transformed into a combination of kinetic, which is moving energy, and dissipated due to the friction. So this is the beginning part. This is kind of part 1. This is position A. This is position B. So putting that together, we'll say at position A we have Eg, and at position B we have Ek plus E dissipated. Once again, let's go back to our notes, and this is really, I don't like the way that showed up, so let's try this again. Eg equals Ek plus E dissipated. So keeping that in mind, we're going to say that mgh equals 1/2 mv squared plus E dissipated. And to be clear, we want to know what the energy dissipated due to friction was. That's this number right here. To be absolutely clear, let's remember our goals in this problem. Our goals and the way we go about that is we remember that energy is a number that doesn't change. So the energy at the beginning of the problem equals the energy at the end. So plugging in our numbers, 24 times 10 times the height that the kid started at, which is 10, equals 1/2 times 24 times 3 squared plus E dissipated. The number one mistake I see people make is that they don't square the numbers that they are working with. So this is going to be, let's see, yeah, so 1,440 joules equals 12 times 9, that's 108, plus E dissipated. And so at the end of this problem, what we're getting is that E dissipated equals 1,440 minus 108 gives us 1,132 joules of dissipated energy. All right. Now, for number 2, we have a similar situation, but now there's no friction. So I can actually take this picture from here and move it down to here. And we'll just note that there is, in fact, no friction. And so what that means, practically speaking, is we can just remove friction from our calculation and even from our little sketch here, which is what I'll do right now. So we'll just get rid of that. There we go. So continuing with this idea, we're going to set up our equations as follows. Eg gets entirely converted into Ek. So we'll set that up as mgh equals 1/2 mv squared. So 24 times 10 times 6 equals 1/2 times 24 times v squared. So this will be 1440 equals 12 times v squared. And when we isolate v, what we'll end up getting is the square root of 120, which is about 10, I'm going to round this up to 11 meters per second. All right, so that's question number 2. Question number 3 is a little bit of a trickier question at first. And I think the confusion here was simply keeping it simple. So here we go. For part A, this is a conservation of momentum problem. So we have a mass of 10 kilograms explodes into 2 pieces. One piece has a mass of 4 kilograms, the other has and moves 6 to the left, and we want to determine the velocity of the second piece. So let's be clear. Let's actually kind of draw a picture here. I'll do that over to the right, and this is what I'll note in part A. So for part A, it's like I have 2 pieces. I have an M1 and an M2. And at the beginning of this problem, U1 equals U2 equals 0. And then at the end of the problem, we have each of these things moving. M1, and just to be clear, let me label one more thing. M1 is 4 kilograms. And M2 is 6 kilograms. Now, let's determine the velocity of the second piece first by looking at our drawing and setting up what we're going to plug into the formula. So we know that we have this thing moving at 6.0 meters to the left, and that it has a mass of 4 kilograms. And for this other piece, we know that its mass is 6 kilograms. And by the way, this is V1. And what we're looking for is V2. So here we go. Let's actually plug in our formula. So M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. Plugging in our numbers. 4 for M1 times 0 plus 6 times 0 equals M1 V1, which is going to be 4.0. Now here's what we're going to do. To the left is what we're going to consider negative. So we'll actually put that in our formula. So that'll be negative 6.0 equals 6 times V2. So we're going to end up getting 0 equals negative 24 plus 6 times V2. So that is going to give us V2 equals 4, sorry, that's not V squared. The 2 should be down here. 4.0 meters per second. Now for part B, the initial kinetic energy is 0. For the final kinetic energy, people really read a lot into this. Let's just keep it simple. The kinetic energy of the first piece, so EK for 1, oh my gosh, let's try this again. EK for piece 1 is 1/2 M1 times V1 squared. People really wanted to read a lot into that. It's just not that complicated. Keep it simple. Just the kinetic energy of that one piece. So 1/2 times M1 is 4 times 6 squared. So that's going to give us 2 times 36, which is 72 for EK1. And for EK of 2 equals 1/2 times M2 times V2 squared, which will be 1/2 times 6 times 4 squared, which is going to give us 48. And so when we add that up, we're going to get a total energy of 120 joules. Where does that energy come from? Most likely from the chemical energy of the explosion. So that's getting converted into kinetic energy. Alright, so that is page 1 on this homework. We'll take a quick look at page 2 and 3 in the next video.